Every wet chemistry analyzer you've worked with mixes liquid reagent with liquid sample in a cuvette. Dry chemistry technology throws that entire model out. No reagent prep, no cuvette, no liquid reagent at all. A single drop of sample lands on a credit card-sized slide, and the reagents are already there, dried into the slide itself, waiting. Precisely, dry chemistry, also called dry slide or thin film analysis, immobilizes all reagents needed for a reaction within solid layers of a small analytical element. The technology traces back to Eastman Kodak's Clinical Diagnostics division, which commercialized the first ectochim analyzer in the late 1970s, adapting photographic film coating technology directly from Kodak's core business. The operational advantages that drove adoption are concrete, not marketing language. Dramatically smaller sample volumes, often just 10 to 50 microliters versus hundreds required by wet methods, room temperature reagent stability measured in months rather than days, and functionally zero liquid reagent waste stream to manage. The basic workflow, end-to-end, is deliberately simple. A metered sample drop is dispensed onto the slide. The sample migrates and reacts through the layered structure. A color or potential change develops. An optical or electrochemical reader measures that change. The instrument's software converts the reading into a reported concentration, the entire reaction, containment, and measurement happening inside one disposable element. Dry slide chemistry isn't one single technology. It splits into two fundamentally different physical mechanisms depending on the analyte. Colorimetric slides measure a light-absorbing color reaction product. Potentiometric slides, used for electrolytes, measure an electrical potential generated across an ion-selective membrane. The optics chapter later in this video applies specifically to the colorimetric type. Electrolyte slides work on entirely different physics. None of this is a free lunch, and being upfront about the trade-offs matters as much as the advantages. Precision can run modestly wider than an optimized wet method. The slides themselves cost more per test. And a genuinely diverse assay menu on one wet chemistry platform can outstrip what's commercially available as dry slides for less common analytes. Turnaround time is where the technology's design philosophy shows most clearly. A typical dry slide colorimetric result develops and reads in under 5 minutes from sample application, a speed advantage that made the technology a natural fit for point-of-care and rapid response testing environments from the beginning. Where this technology actually lives today spans a wide operational range: point-of-care and emergency department analyzers, veterinary and clinic chemistry systems, some hospital core laboratories running high-volume routine panels, and blood gas and critical care analyzers using the potentiometric electrolyte variant specifically. A colorimetric dry slide is a genuine engineered laminate, typically 4 to 5 distinct functional layers bonded together, each performing one specific job in sequence as the sample migrates downward through the structure. The spreading layer sits on top, and its job is purely physical, not chemical, distributing the sample drop evenly and rapidly across the slide's full reactive area. Typically a microporous, non-woven or woven fabric structure, it also performs a critical filtering function, screening out red and white blood cells, preventing them from ever reaching the reagent layers beneath. The indicator layer, immediately beneath the reagent layer, is where the reaction's end product actually becomes visible and measurable. The dye or chromophore generated by the enzymatic reaction concentrates here, its color intensity directly proportional to how much analyte was present in the original sample. The support layer, the base of the whole structure, is optically clear and mechanically rigid, usually a polyester film, existing purely to give the laminate physical structure and, critically, to let the reflectance reader's light beam pass through cleanly to illuminate the indicator layer from behind. Electrolyte slides swap this entire architecture for something different: a semi-permeable membrane and an ion-selective electrode layer, physically separating and detecting specific ions rather than generating color. Mixing up the two slide families' handling requirements, treating a potentiometric electrolyte slide like a colorimetric one, is a real, documented source of erroneous results in less experienced hands. Slide storage and handling deserve the same rigor as any reagent, because these are, fundamentally, dried reagents. Humidity exposure rehydrates and degrades the dried chemistry prematurely. Temperature excursions above the validated storage range accelerate enzyme denaturation within the reagent layer. And expired slides, even if they visually look intact, can carry meaningfully degraded reaction kinetics. Handling discipline that protects slide integrity. Concretely, keep the desiccant sealed pouch or cartridge closed until immediately before use. Minimize the time a slide sits exposed to ambient air and light before sample application. Respect the labeled storage temperature without exception, and never use a slide past its printed expiry regardless of how it looks. Manufacturing consistency across a slide lot matters more here than in wet chemistry, precisely because each slide is a complete, self-contained analytical system rather than one component mixed with fresh reagent at test time. A coating thickness variation of even a few microns in the reagent layer can shift the reaction's kinetics measurably. The architectural takeaway: every layer in a dry slide exists to solve one specific problem in sequence: spreading and filtering, reacting, indicating, and supporting, and understanding that sequence is what makes troubleshooting a failed slide reading tractable instead of a guessing game. If this level of technical depth on the underlying chemistry is useful, subscribing keeps this series coming. The moment a sample drop contacts the spreading layer, diffusion, not active mixing, drives everything that follows. Water and dissolved analyte move downward through each layer purely by capillary action and concentration gradient, rehydrating dried reagent as they go, with no pipetting, no vortexing, no mechanical agitation anywhere in the process. Reaction kinetics in this confined, diffusion-limited environment behave differently from an open cuvette. Timing matters intensely. Most colorimetric slides are read at a fixed, tightly controlled endpoint time, because the color continues developing after the theoretical reaction endpoint. Reading too early undercalls the true concentration. Reading too late overcalls it. The chemistry types packed into these reagent layers span the same breadth as wet chemistry, just reformatted for a solid phase format. Enzymatic reactions for glucose and cholesterol, coupled enzyme cascades for creatinine and urea, and colorimetric complexation reactions for electrolyte-adjacent analytes and specific proteins. One genuine chemistry-level advantage worth naming directly, because the spreading layer physically filters out cells and larger interfering particles, and because the reaction occurs in a thin, controlled film rather than a bulk liquid, dry slide chemistry shows real, documented resistance to hemolysis and turbidity interference compared to equivalent wet methods, though it is not immune to icterus or lipemia entirely. Temperature control during the reaction itself is handled by the instrument's incubation block, not the slide, and it's tightly regulated for exactly the same reason it matters in wet chemistry. Enzymatic reaction rates are temperature dependent, and even a 1 or 2 degree deviation from the validated incubation temperature measurably shifts the reaction's timing and final color intensity. When a slide reading looks unexpectedly off, the chemistry-level troubleshooting sequence starts with timing and temperature before anything else. Confirm the read occurred within the validated endpoint window, confirm the incubation block held its set temperature throughout, and only then move to investigating the slide lot or sample itself. The chemistry-level principle worth carrying forward: this is real, kinetically sensitive chemistry happening in a solid film, not a static color card. Timing and temperature control matter exactly as much here as in any wet phase reaction, arguably more, because there's no opportunity to remix or retime once the reaction begins. Wet chemistry reads absorbance. Light passes straight through a clear liquid sample, and the instrument measures how much light made it out the other side. A dry slide is opaque. Light cannot pass through it at all. So dry chemistry reads reflectance instead. Light shines onto the slide surface, and the instrument measures how much bounces back. Mechanically, a light source, typically an LED at a specific wavelength matched to the reaction's chromophore, illuminates the slide from below through the clear support layer. Light passes through, reflects off the colored indicator layer, and returns back through the support layer to a photodetector. The support layer's optical clarity from earlier is exactly what makes this geometry work. Here's the genuinely advanced piece most explainers skip entirely. Reflectance and concentration are not linearly related the way absorbance and concentration are in wet chemistry. The relationship follows the Kubelka-Munk function, which relates reflectance to a ratio of the layer's absorption and scattering coefficients, and that relationship is fundamentally curved, not straight. Quick pause. If this breakdown is helping you, take a second to hit like and subscribe. It genuinely takes a lot of effort to make videos like this, and your support keeps them coming. In practice, this is exactly why dry slide calibration curves are rarely simple straight lines. Instrument software applies the Kubelka-Munk transformation, or an empirically derived equivalent, to convert raw reflectance into a linearized concentration value, which is also exactly why forcing dry slide data into a simple linear calibration model, as covered in the broader calibration discussion, would be a genuine chemistry-level mistake here. Wavelength selection matters as precisely here as anywhere in spectrophotometry. The reading LED or filter is matched to the specific chromophore's peak absorption wavelength for that analyte's chemistry, and using the wrong wavelength, a mismatched slide type loaded with the wrong reagent card, for instance, produces a reading that's simply meaningless, not just slightly off. Slide surface geometry itself introduces optical variables that a liquid cuvette simply doesn't have. Surface texture, slight thickness variation, and even minor curling or warping of the slide can scatter light unpredictably. Manufacturing tolerances on slide flatness and surface finish are tightly controlled specifically to keep this scatter-related noise below the instrument's detection threshold. Keeping the optical reading path itself trustworthy, practically. Keep the reader's optical window clean and free of dust or fingerprints. Verify the reader's own reflectance calibration against a certified reflectance standard per the manufacturer's schedule. And never bend, fold, or handle a slide by its reading surface before or after measurement. The optics level takeaway: reflectance photometry isn't just absorbance photometry pointed at a solid instead of a liquid. It's a genuinely different measurement physics with its own non-linear math, its own wavelength discipline, and its own sources of optical noise to control. Almost to the practical core, if this is useful for your bench work, alike helps this reach more working lab professionals. This is where dry slide systems genuinely diverge from the multi-point calibration approach covered earlier for wet chemistry analyzers. Most dry slide platforms don't ask you to run a full multi-point calibration curve for every reagent lot at all. They use a manufacturer-supplied master curve instead, encoded directly into the slide lot's packaging or a barcode. The master curve concept, precisely, the manufacturer characterizes the full reflectance to concentration relationship for a given reagent formulation using extensive internal calibration data across many production lots, encodes that relationship into the slide packaging or instrument software, and your instrument then applies that pre-built curve directly to your slide lot. No full multi-point run required on your end. This doesn't mean you're off the hook for calibration entirely. It shifts the burden from full curve building to single-point verification. Most systems still require running one or more calibrator or control materials at the start of each new lot, confirming that this specific lot's master curve is actually tracking correctly on this specific instrument before releasing patient results. If that lot verification check fails, the troubleshooting logic runs differently than the shift or rotation or outlier taxonomy from the wet chemistry calibration discussion. Because you're not diagnosing your own regression fit, you're diagnosing whether the manufacturer's master curve genuinely applies to your specific slide lot and instrument, or whether something in your local storage, handling, or instrument condition has shifted. Daily and per lot QC still applies in full force, running control materials of known value through the slides exactly as you would controls through a wet chemistry method, plotted on Levy-Jennings charts and evaluated against Westgard rules identically to everything covered earlier in this series. The underlying quality framework doesn't change, only how the initial curve was built. This master curve model carries a real practical upside worth naming directly. Dramatically less hands-on calibration time per lot change compared to running a full multi-point curve, which matters enormously in point-of-care and high-throughput settings where an analyzer sitting idle during calibration has a real operational cost. The calibration level principle worth carrying. Less on-site calibration burden is not the same as less accountability. You're still responsible for verifying that a lot's master curve actually performs correctly on your instrument, with your patient population, before you trust a single result from it. Laid out systematically, precision studies comparing dry slide and optimized wet chemistry methods on the same analyte typically show dry slide coefficients of variation running modestly wider, often by a fractional percentage point, a real but usually clinically manageable trade-off against the operational advantages covered earlier. Weighed as a genuine trade-off rather than a marketing pitch, dry chemistry wins decisively on speed, sample volume, reagent stability, and operational simplicity. Wet chemistry generally wins on raw precision, assay menu breadth, and cost per test at high volume, which is exactly why most large core laboratories still run wet chemistry platforms as their primary workhorse. The failure mode's worth knowing cold, because they're specific to this technology and won't show up in generic wet chemistry troubleshooting training. Incomplete sample spreading leaving dry patches on the reactive area, air bubbles trapped beneath the spreading layer blocking migration, and slide curling from improper storage humidity distorting the optical reading geometry entirely. A full technical scenario, not a patient one. A point-of-care glucose reading returns an error flag citing insufficient spread on roughly 1 in 20 slides from a specific box, with no pattern by operator and no issue on other glucose slide boxes in stock. Narrowing the search immediately to that specific box's storage or manufacturing history rather than technique. Investigation traces the affected box to a shipping pallet stored briefly, near a loading dock door during an unusually humid week, subtly compromising the spreading layer's wicking performance on just that carton without visibly damaging the packaging. Quarantining and replacing that specific box, while leaving the rest of the lot in service, resolved the error rate to baseline immediately. The troubleshooting discipline worth internalizing. Dry slide failures are frequently localized. One box, one storage event, one shipment, rather than systemic and isolating scope before escalating broadly saves real time and avoids unnecessarily pulling an entire lot from service. Building institutional resilience against exactly this kind of localized failure. Log lot and box numbers against every error flag, not just the error type, so patterns like this become visible immediately rather than requiring a special investigation. Track error rates by box, not just by lot, whenever your inventory system allows it. The real-world footprint of this technology spans a genuinely wide geography and setting range. Emergency departments and urgent care clinics running rapid basic metabolic panels, veterinary practices worldwide using compact in-clinic analyzers, remote and resource-limited settings where reagent refrigeration and water access are unreliable, and blood gas analyzers in nearly every intensive care unit using the potentiometric electrolyte variant. Selecting dry slide technology for a given setting comes down to a genuinely practical checklist. Is testing volume low to moderate rather than high throughput? Is rapid turnaround more clinically valuable than marginal precision gains? Is reagent refrigeration infrastructure unreliable or unavailable? And is the assay menu required actually covered by available slide chemistries? Everything this series has covered elsewhere still applies fully to a dry slide platform. Sigma metrics, Westgard QC rules, EQA participation, and calibration verification discipline all sit on top of this technology exactly as they would on any wet chemistry analyzer. The slide changes the measurement mechanism underneath. It doesn't change the quality system built on top of it, bringing it all together into a working reference. Understand which slide family you're handling, colorimetric or potentiometric, before troubleshooting anything. Respect storage, humidity, and temperature as rigorously as any liquid reagent. Trust the master curve, but verify it per lot. And remember that reflectance photometry is genuinely different physics from the absorbance readings you're used to. One misconception worth retiring: dry chemistry does not mean lower quality or less rigorous chemistry. It means the exact same underlying enzymatic and chemical reactions as wet methods, reformatted into a solid phase film with genuinely different, and in several ways more resistant, measurement physics. Understanding dry slide technology from the layer architecture up through the optics and the calibration model changes how you troubleshoot it entirely, from guessing at an unexplained result to reasoning through exactly which layer, which physics, or which lot-specific factor is actually responsible. Final recap. Dry chemistry immobilizes reagents in a multilayer slide instead of using liquid reagent in a cuvette. The spreading, reagent, indicator, and support layers each perform one distinct function. Reflectance photometry, not absorbance, reads the result, following the non-linear Kubelka-Munk relationship. And most dry slide systems use a manufacturer master curve with per-lot verification rather than a full multi-point calibration. Here are the key references and sources for this video. Thanks so much for watching. If this helped, like the video and subscribe for more clear, simple explainers, and I'll see you in the next one.